Yeah, thanks everyone. Thanks for having me here today, and thanks to Bob Drew and Lily for the introduction. Uh, before the talk starts, I need to first apologize that my flight yesterday was delayed by a few hours, and one thing led to another. I barely had any sleep last night. So I'm gonna try my best to speak loud, such that people sitting behind can still hear me. I know I should sound more excited than I probably do today. But I mean, still, I want to emphasize that no matter how I sound like, I mean, I'm really excited to come here and give a talk. Okay. Yeah, the talk is about the language models for reasoning. We kind of live in the age of large language models. And starting from the end of 2022, everyone has been talking about large language models like ChatGPT, and we know it has many parameters, and we know it shows up with really mind-blowing abilities, like sweeping all the possible benchmarks in the community of natural language processing. And more than that, we know there are even people reporting it shows some human-like intelligence, like GPT-4, which is a later version of ChatGPT, is reported to achieve high scores on professional tests like bar exams. Well, I was also impressed by this kind of behavior. So I was very curious to test ChatGPT with a puzzle that I enjoyed solving when I was a kid. The puzzle is about who lives in the greenhouse. We have three statements talking about three people of different nationalities and living in different houses, and each house have a different color. We know the Spanish lives directly to the right of the red house, the Italian lives in the house 2, and Norwegian lives in the house 3. And the puzzle is given these clues. We want the tester, we want the testee to figure out who lives in the greenhouse. Now let's try to do this puzzle by ourselves. Let's start. I try to visualize this statement, and we know this is the current clues we have. So from these statements, we can try to draw one or multiple statement existing clues from the current. Let's call it a theory. We can draw a set of clues from the theory and deduce some new conclusions, and we can keep going and extend the theory. For example, from the first statement, we know the Spanish lives either in house 2 or house 3. It cannot live in house 1. And combine this new deduction with Italian lives in house 2, we know Spanish must live in house 3 because house 2 has been taken. And combining this new deduction with Italian lives in house 2 and Norwegian lives in the blue house, we know Norwegian lives in house 1 because that's the only one left. We know this house is blue. And we can also combine this deduction with the previous statement, and we know the house 2 is red. And because we know Italian lives in house 2, and we know Italian lives in the red house. Now, the only one left is the third house, which is where Spanish lives, so that is green. It's not trivial. It takes some kind of thinking to figure it out, but we can indeed figure it out. And once we do, no matter how many times we repeat, we can get it correctly. I tried it with large language models. And this experiment was done right when I was making this talk. And I tried with the GPT-4 version, the most state-of-the-art version. And I try to prompt with a step-by-step way such that it can roll out some kind of reasoning, and is so far the most popular, widely accepted, sophisticated way, a good way to prompt a large language model. And I tried it once. The large language model said, the GPT says, and the Italian lives in the greenhouse, which we know is wrong. And I think it's kind of unfair. I only asked it once, right? What if I just initiate a new window and ask the same question again? And because a large language model is a probabilistic model, as long as you don't set the temperature to be 0, you can roll multiple times, it may give you different answers. And the second time, it gets it right. It says Spanish, it lives in the greenhouse. How many times is it right overall? As of November 2023, I tried GPT-4 multiple times, and 50% of the times it get it correct. So why this problem matters? Why do we want to care this problem? Because these problems are very simple representations of a fundamental problem in AI, which is reasoning. And reasoning is an overloaded word, and many papers talk about different kinds of reasoning, like common sense reasoning, numerical reasoning. The reasoning I specifically want to talk about is a kind of reasoning that you draw new facts from the old facts. And this fundamental reasoning ability is required for solving many more complicated problems than the logical puzzles that I just showed. For example, in maths, we start with a really small set of axioms, but we apply logic to this set of axioms, and we can draw many theorems, write books, many books of mathematical knowledges. And if we want, automatically, we want an AI mathematician that can help us prove new theorems, we need the AI agent to possess this kind of reasoning ability, deductive reasoning ability. And another kind of reasoning problem is to regard the events that have happened in the past as the old facts, and try to reason about the new fact, which is the events that are about to happen in the future. And with this kind of reasoning, we can once a model is capable to do this kind of reasoning, it can potentially read the events that happened in the past and reason about what will happen in the future, and possibly respond to this kind of predictions. My research is based now. Maybe I should take this opportunity to give a more detailed introduction to myself. My research is basically about the reasoning, or more precisely, it's about developing machine learning methods for reasoning about the world, the real world. And my dream is to enable intelligent agents with strong reasoning capacities that can democratize technology to every corner of the world. And an example is for example, the educational AI assistant, which can possibly read past the events happening to a student, maybe what tests or lessons have been taken and what are the score on the test. So it can predict future events of the student. And then based on the prediction, we can the agent can suggest future lessons and tests to take and when to take them, with the goal to help the student to achieve a fruitful and enjoyable learning experience. And with this research goal, my research broadly spans natural language processing and the event sequence modeling. And in this talk, I will focus on presenting two of my recent papers in reasoning with large language models. We have seen an example of the logic puzzle that language models still cannot 100% get it 100% correct. And now maybe it's time to ask the question: are large language models fundamentally the right solvers for complex reasoning problems? To answer this question, we probably better step back a little bit and review how large language models learn and do inference. Large language models learn to predict next token given the left context. For example, taking the string of this example, it first tokenizes the string into a sequence of tokens, augmented by a beginning of the sequence token, and these tokens are fed into the language model, one token after another, and the model computes the probability distribution of each token given its left context. Then the training objective is a summation of their log probabilities. And once we have learned this distribution, and during inference, we can draw each token given this distribution and its left context by sampling or searching according to this learned distribution. What can model actually learn by just predicting the next token? One thing now, like the consensus thing language model can learn at least is the pattern of the text. Like I give you a piece of the text, and what will be the distribution of the future tokens in the text. Well, I guess that's something the community has agreed that the language model can well capture it. But there's still, as I know, there is still no consensus on whether language model can learn the underlying dynamics that generate the text. What I mean by underlying dynamics, I mean, for example, when I write a novel, I probably already have the entire plot in my mind. When I write down the first chapter, I probably already think ahead into the chapter 10 and jump back to write the first chapter given what I want happened in chapter 10. And that is not capturing the left context of the novel. And another example is how people argue with each other and trying to trying to convince each other of something. And to do that, we use language as a weapon. And we try to anticipate what will be the outcome from your side once I say certain things, such that I can pick the right thing to say at the current moment. And another thing is math. For each given theorem, we know there are multiple ways to prove there are usually multiple ways to prove a single theorem. And the way you actually written down the proof, the order of the lemmas you written down in the proof may not actually reflect the way you figure out the proof in your mind. So that is something is not obviously embedded in the surface text. And it is definitely open question like whether language model can learn that by simply learning to predict the next token. Should we be optimistic or pessimistic? At this stage, there are definitely like arguments and debates between the two sets. I know there are one group, we know like there are one group of people believe, I mean, ultimate AGI will come as long as we scale up GPT-3 like 1,000 more times starting from now. And there are also people thinking like all the current effort on large language models is actually an effort on the off-ramp of the real AGI. Well, I don't know whether people can figure out the answer to these questions within this year or next year or within the decade. But well, I'm personally bothered by thinking of these questions and couldn't draw a meaningful conclusion by myself. I step back a little bit and start thinking of another problem. What if both sides step back a little bit and say, maybe what if large language model is strong enough to be a part of the ultimate AGI, like 100 years in about 100 years? But what if it is not the only component of AGI? What if there are other fundamental components that work together with large language model? Then the question is, what are other components be? And how do they work together? And that is the question I have been thinking over the past year. And sorry, I got a little late on the slide. So basically, if that is really the future, then these two questions are what I've been thinking over the past year. What if like the whole brain of future AGI is like something made up of Lego blocks, and large language model is one of the Lego blocks. And then we have other kind of Lego blocks, and what are them? What are they? And how should they be assembled? And in this talk, I'm going to present some recent progress that my collaborators and I have made while thinking about these questions. I'm going to first show how to combine large language models with classical logical inference methods to build strong text-based logical reasoning systems. And then I will show how to generalize this large language model as Lego principle to other areas like event sequence model. The first work is done with my students at TDSC and my collaborators at WeChat AI. And in this work, we develop a text-based logical reasoning system called LEAP, which performs explicit look-ahead planning during logical inference. Yeah, this slide is a little bit head-wavy, but I'm gonna get it concrete very soon. So let me first introduce the problem. The problem is very like the logic example at the beginning. But the example I made here is very simple to just use it as a pedagogical example to walk through the method I'm going to introduce. The problem is just logical inference, given a set of statements as we see at the beginning, and we want to test. We want to determine whether a given hypothesis or a given goal is correct. In this case, we know Eva is a queen, and Eva is just, and just queens are good, and good people are blessed. And we want to know Eva is blessed. This example is kind of obvious. So if we use language, when we think of this, when we think of this for problems, I mean the kind of the reasoning process, like how do we combine a subset of the statements from the theory and what step by step draw the final conclusions. So regardless of whether large language models have the capacity to learn it by just reading some surface text. And we know there has been a rich body of work dedicated on this kind of problem, on this back in 1960s, but made up the formal, I mean the body of the formal logic work developed by the logicians in 1960s and on this kind of problem. So maybe this can be one of the useful Lego blocks to be assembled together with large language models. And suppose, and while thinking of that, it seems a little bit useful. Is useful to give a little bit overview, a recap on how formal logic works. In a formal logic system, will first convert natural logic statements into their formal logic version. And for example, now I see these three statements are converted into which I represent with first order logic syntax, where we use the blue color to denote the facts which we know are true, and I use the orange color to denote the goal or the hypothesis, which look like a fact, but its truth value is to be determined. The rest of the clues are kind of implies some kind of if-then relations. So their first order logic version have variable x, meaning that this statement can apply to all the facts that meet the conditions. And such a formal logic statement is called a rule, and we use green color to denote the rules. And for this example, given the two facts already meet the condition of the first rule, so we can just apply the first rule to these facts and deduce that Eva is good, which is a new fact. And this new fact is kind of theory. Now the theory has a new fact that becomes larger. And this deduction has nothing to do with the goal yet. So we keep going. And as we can see, the new deduction match the condition of the second rule. So we can apply the rule to this deduction and draw a new deduction, which is plus the Eva, which exactly matches the goal. So we say, okay, it is good. It's possible that sometimes the given hypothesis or goal cannot be proved at all. And in this case, we keep extending the theory step by step until it couldn't be extended further. But if there's still no new deductions can match the goal, then we say this goal may be not provable. This simple method, also formally called the forward chaining method, can apply to theories of any number of facts and rules, and possibly draw a really large deduction graph. And for any new deduction generated through this process, we can trace back from that deduction until we reach all the relevant basic facts. And the backward trace, and we call the backward trace the provenance of deduction, or in other words, the proof of deduction. And sometimes we may have many steps of reasoning and we construct a really large graph, but the size of the graph will be bounded because we have finite number of known facts and rules. Our system, the system leap we develop in this work follows the general procedure of this rule-based system because it seems to capture how humans actually do logical reasoning step by step. But the difference is now we use large language model. We use large language model to do each step of pattern matching and deduction. And what large language model brings is the flexibility in handling languages. Now we don't have to exactly match the certain facts to rules of certain structure. As large language models can flexibly combine facts that look somehow compatible with each other and draw a new deduction in free language form. But the whole system still do multi-step reasoning, just like the rule-based system. At each step, the language model basically makes two atomic decisions. The first decision is to select the combination of the old facts from the theory, which one can possibly draw a new statement. And this resembles the pattern matching step in the formal logic system. And the second atomic decision is simply to deduce a new statement from the selected statements. Each decision is made by prompting a large language model. And in context, the prompting has been a really widely adopted technique to instruct the language model to do some downstream tasks. And here, our downstream task is to select the relevant statements and make meaningful deduction. At each step, I'm going to go through this very quickly. At each step, the language model reads the current theory together with a prompt that includes the task definition and demonstrations. And we also fit Go into the language model such that it's going to attempt to select the statements that are relevant to the goal. Then by reading this whole prompt, the language model learns to make the selections from the theory. Similarly, we prompt the language model to draw logically plausible deduction from the selected statements. If language models are able to make perfect selection and deduction decisions at each step, then our system will be able to generate a correct and concise reasoning graph like this. But the question is, can large language models actually make good decisions? As we keep seeing throughout the talk, large language models are probabilistic models. And it's possible that there is a mismatch between the training and the deployment. So even with very careful prompts, it's possible that many not so good selections and deductions are still quite probable under the large language model. Then as a result, the language model may propose many probable selections and deductions that are not that seem to make sense, but not logically useful for proving the goal. For example, it may combine x2 and x3 and draw Eva is good if she's a queen. It's a reasonable deduction, but it's more complex than what we desire. Of course, it may also select the x3 and x4, deducing Eva is blessed if Eva is a just queen. And of course, it may select s1 and x2, which we intuitively desire, so that a reasonable and concise deduction can be drawn like Eva is a just queen. But even given this desirable selection, language models may still draw deductions that are not ideal, like some of the deductions may mean the same thing, but a little less concise. And like Eva is a queen, but she's just, and some may be incorrect in the sense that it loses key information, like it's just a repetition of one of the inputs. If we keep all the language model proposed selections and deductions at each step, we will easily end up with a very large graph that is very expensive to handle. So then in Leap, what we do is we print a large graph by only keeping the most promising selection and deductions at each step. How do we measure promising? We measure promising by looking ahead into the future steps of each large language model proposed option. For example, this example shows a selection step, and now large language model has proposed a number of selections. And for each of them, we can roll out a few future steps of reasoning. Then for each future deduction on the rollout, we use a verification model to score how likely it will prove the goal. And then we take the maximum of these scores of deductions, and we use it as a proof score of this selection, indicating how likely it will lead to a sequence of useful future steps. The verification model is simply a Alberta model pre-trained on a natural language inference dataset, where it takes a pair of sentences and gives a score between 0 and 1, representing how probable deduction can directly prove the goal without any other information. And given this proof score, we combine it with the probability of the selection and the language model to compute a final selection score for this selection. And we repeat this procedure we repeat this look-ahead procedure for each language model proposed selection, and we only keep the ones with the highest score. And for each selection we keep, we draw multiple possible deductions from the proposed language model. And then for each possible deduction, we perform the same kind of look-ahead planning and roll out future reasoning steps. Then we score each deduction with a verification model again, and just like we did for the selection step, and we got the proof score for the deduction. We combine the language model probability of the deduction, and we get the deduction score, and we do the same thing for all the possible deductions, and we only keep the highest score ones. So far, so good. We can just keep doing this to the future steps and repeat this procedure of look-ahead planning, and ending up with a much smaller and manageable reasoning graph. Like in a graph given by the rule-based system, we can trace back from a language model generated deduction to find out its entire provenance, or in other words, its proof. And each proof is scored in the same way as we score each look-ahead rollout. And we pick the highest score proof as a final output. If the score is high, we say the goal is proved from the theory. And if the score is low, then we say the goal cannot be proved from the theory. So far,
so from like that, you said the deduction score which selections you keep is some.
We can't hear the question.
Oh.
Can you repeat the question, please?
Because the language model, from its extensive pre-training, it provides a quite reasonable prior. And that's first. And second, the look ahead relies on a pre-trained model, which is still a model, not an oracle. So it may be exploited by the algorithm. So having a balance between these two scores possibly gives you a sweet point to find a sweet point, better than the two extreme. It's actually not. I use plus here to basically show combination. Maybe I should use another formula. Yeah. So yeah. Yes. I guess so. In our.
Can you repeat the question, please?
The whole as we will show shortly in the experiments, the whole framework works with, we try the framework with a small language model at its core and the large language model. For the small language model, it can be as small as 60 million parameters, just GPT T5. And for the large language model, we tried GPT 3.5, which was the state of the art at the time we work on this paper. And for the small language model, we do see on the depth side between the balancing parameter between these two scores a little bit, we get better results. And for the large language model, because they are black boxes, so the language model probabilities we just set it to 0. And for the large language models, we highly rely on just the proof score. But I sweep this under the rug for this talk. Thanks for asking. Sure, definitely. Tree binary means it's actually a hyperparameter you can check. You can see I want to combine less than 3 or less than 4. We try less than 2. In our experiments, we evaluated both the small language model version and the large language model version. And for the small language model version, we work on a data set called the entailment band, which gives you the theories and the goals similar to the examples we have seen so far in the talk, but it's human annotated and about animals and plants in the world. And it's split into training, dev, and test data. And on this data set, we evaluate a small language model version of our framework. And we use T5 small, which has only 60 million parameters. and we learn soft prompts, which means we train the input embeddings of the of some prefix tokens in the prompts. But the parameters, the number of parameters is actually very small. It's only 10,000. It's tiny, and we want to use this experiment setting as a pedagogical study to see whether a small model, whether such a system with small language model can be competitive to a large language model like GPT-3. That's the first set of experiments we did. Sounds a little bit like Don Quixote. We evaluate this method in a multi-choice QA setting, where each theory has 3 negative choices that are sampled from other theories. And in this setting, we use our system to score each choice, and we choose the highest scored choice as the answer. And here are the results. The leftmost blue bar is the score of our system. It achieves almost a 90, higher than GPT-3, 0 shot. And of course, GPT-3 0 shot is kind of a weak baseline, and stronger baseline should be GPT-3 5 shot and GPT-3 chain of thought prompting. But as we can see, Leap is still performed somehow competitive to 5 shot and chain of thought prompting, considering the fact that Leap only have 60 million parameters, and the GPT-3 has a lot of more parameters and a lot more pre-training. This is this is the small model experiments, and the second set is a large model experiment, where we evaluate. In this setting, we evaluate on the prompt QA data. Prompt QA data is a data similar to entailment bank, but much more challenging to large language model like ChatGPT, because the theories and goals in the data set are constructed to be about fictional characters of fictional features, because of large language models have undergone extensive pre-training. So they have been heavily biased towards the real world we live in. Then asking questions about fictional characters maybe should be harder for them. And on this data set, we use GPT 3.5 as the core language model. And on this data set, we follow the paper that proposed the data set to use binary classification for each given theory and goal. We use the Leap system to return a scored proof. And then we use the GPT 3.5 to read the Leap proof and give a final true or false output. And the last step is similar to any prompting technique like chain of thought prompting, except that the reasoning is generated by Leap, but not the language model itself. We evaluated in this setting with varying depths, where depths means the number of ground truth reasoning steps. When a test has a larger depth, when a test case has a larger depth, it means it is more difficult. And as we can see, out here, blue bar is still ours, and purple bar is GPT 3.5 with chain of thought prompting, and the red bar is a method called selection inference method, published by DeepMind earlier this year, which is very similar to the version of our Leap system without look-ahead planning. And as we can see, in all the cases, the performance of each single method will downgrade as the depths become larger, because the cases will become more difficult. But our method consistently and significantly outperform these strong baselines. Right, yeah, this is the end of the first part of the talk. And so far, we have seen that using large language models as a building block for logical system, for logical reasoning system, it seems to be a promising way to tackle complex reasoning problems in natural language processing. And for the second part of the talk, I want to answer the question like, can we generalize this idea out of the natural language processing domain, but some other domains in general AI? And the answer is yes, as we will see shortly. And that is what I will discuss next in this talk. And in the next part, we will show how this idea can generalize to event sequence modeling, or in other words, time series modeling, where we integrate the language model with a classical event sequence modeling framework and advance the state of the art in that area.
Is this a good time to ask questions
That
about the
sequence
first
modeling
part?
is a lot like language modeling. Its focus is to build probabilistic models over sequences of tokens. But here, sure. Oh, yeah.
Like Russ, I have questions about the first segment before you get on to the second segment. So two general questions, but a comment first. I greatly appreciate
Sure.
delivering the intersection of attempting to do logical reasoning.
For those of you on Zoom, can you hear me speaking?
I hear
Yeah,
you.
okay. If you're on Zoom today, normally we'd be able to hear your voice if you'd like to ask a question, but today we actually can't hear you. So if you don't mind to just type your questions into the chat, and then I can read them out for the speaker. It looks to me like maybe Russ had a question.
Yeah, but so I'm going to wait for Randy, but can the speaker hear us at all?
Yeah,
right now?
sorry, I can't hear you. Can you maybe type it into the chat? Sorry about that. And Randy has a question as well. So if you could both just type it out for me, and then I will read it to the speaker. We have a different audio setup today, so just give me a second. They're typing now.
Cool.
So I finished my question, Bobby Joe.
Oh,
I'll get back to it.
hi, sorry. Okay, so we had another question from the audience in the meantime. Do you mind just holding it for a moment? Yeah. Okay, good news, Russ. We actually fixed the audio and Randy, so we are able to hear you now. Yay. So if you want to just go ahead, maybe Russ first and then Randy, and then we'll take the question from the audience after that. Okay.
Thank you. So a very interesting proposal. I really enjoyed hearing the description. When we talk about the logical inference, are you just looking at horn clauses, just things for which reasoning is efficient? Or are you looking at general propositional reasoning?
This is a great question. I think when developing a method, what we aim to do is to handle the general logic reasoning. So maybe not even propositional or first order logic, because language by itself is more ambiguous and has higher variability, so it's more fuzzy. But in the experiments, we work with the existing data set, and some of them are synthesized from rule-based, some are synthesized from the rule-based formal logic-based statements, and some are annotated by human with certain structure restriction. So, so in that sense, there is still a gap between what we aim to do with the method and what we actually implemented with given the practical constraint in the community. I hope this answers your question. I think this actually also relates to the question asked by one of the audience here in the room. Someone asked like whether we whether we solve the kind of a logical puzzle at the beginning of the talk. We haven't done that experiments. In our paper, we didn't do the experiments because we want to work with the existing data set like the community has already been evaluating on. So we have we have a clear set of baselines to compare with. And the second is that's basically the main reason I think. So and we do have ongoing work developing methods that handle fundamentally more complicated, for example, larger theory with more distractors. And in that, in that project, we work with data set and not only like the example at the beginning of the talk, but also other kind of logical puzzles, like for example, Tower of Hanoi, or more formal logics or some kind of more math-like thing, like SAT problems, SAT binary classification for SAT problems. So actually for this paper, it's like the initial attempt that we do in this direction. And we try to simplify the experiment setting for better analysis and understanding from our own end. And it's a little sad that we haven't done the opening example, but we're moving towards that.
So again, people also do puzzles like that poorly. People do very well with horn clauses, with rule-based systems. When you go beyond rule-based systems, people have a hard time also. And if you're trying to model what people do, which is what LLMs typically are trying to do, it might make sense to just do horn clauses or things simple. That was just good. But thank you for your answer.
Yeah. Yes, I agree with that. But there is, I agree. First, I agree with that. And the second is, I do believe language model has the capacity to, in some sense, do this better than humans can do. Just like how neural networks can do many tasks, like detecting objects, like than humans do. For the logical puzzle, for the kind of logical puzzle I showed at the beginning, I agree that it can be very hard. For example, if you extend the logical puzzle to incorporate 5 or 6 statements with not only nationality and the color of the house, but also the pet they have and some other features of the house, then if you search instant puzzle on Wikipedia, you will find a Wikipedia page saying instant puzzle, which basically just that logic house puzzle with 5 statements can only be solved by less than 10% of the takers.
Yeah, well, horn clauses are relatively easy. When it goes beyond horn clauses, things get more complicated. People do it poorly, and reasoning is NP hard if not undecidable. There's a reason for that. These are examples. But good, thank you. Thank you very much. I said Randy asked his questions, but thank you for your comments.
Yeah, thank you.
Hongyuan, I have 2 questions which probably just beg partly a similar question to Russ's. The first one is that you repeatedly spoke about LLMs as probabilistic, but they're not probable, they're statistical. And the reason that I say that is that in the spectrum of sort of the 3 pillars of what's been described as neurosymbolic reasoning, that is logical, probabilistic, and statistical. The reason LLMs aren't probabilistic is that everything is dependent on everything, and you can't make corrections based on saying things are independent from another. So the color of the Italian's hair is independent of which house he lives in. You can't tell an LLM that because they're recording every weighted relationship as dependent relationships, which is typically at least one of the source of errors. So in doing this, then consider with the basis of Russ's question, the applications of logic in AI have evolved from what you might say is good old-fashioned deductive logic of any kind, all the way from propositional logic through horn clauses, first-order logic, higher-order logic. And one of the things that your question of the intersection of LLMs and reasoning raises is maybe one wants to use more sophisticated logical reasoning models. For example, hypothetical or abductive reasoning is a necessary component in all of medicine and in all of legal reasoning in areas that I've worked in. Do you see extending things in that direction? And maybe a comment on probabilistic versus statistical.
Basically, I heard 2 questions, and the first is the possible applicability of the method of our method on real domain, logic-heavy domains like legal and medical. And the second is my comment on the argument about the probabilistic and the statistical, right?
Well, in the first one, it's not a question of which logic is appropriate. It's a question that the use of logic has adapted. So we've gone from deductive to non-monotonic, to analogical reasoning, to hypothetical reasoning. All of those are motivated by having a more sophisticated position, and your position, as Russ pointed out, looks like horn clauses where you can't even state a contradiction, for example. So what's your projection of how to combine that?
Oh, there is a rich literature and rich arsenal of formal logical methods on handling logical problems, and in COPS there are different methods that focus on different aspects of what you just said.
Yes.
And in this paper, and I believe there are plenty of research opportunities trying to figure out how to combine large language model with those methods, and yeah, whether we can combine large language model with those methods and how to do so. And in this, and in the current work, we focus on one of the reasoning, which is basically just deductive. I'm not saying like this framework can do the problem that are supposed to be done by other kind of reasoning. This is more of a concrete method, which is a forward chaining, forward chaining method. Yeah, right. Combined with large language model. So it is. And so
the other question is simpler to answer. That it's that I would concede that your perspective on LLMs as probabilistic models is possibly accurate only if I can make a statement about saying which dependencies hold and which don't. So like the color of the Italian's hair is independent of the house he lives in. I can't make those statements because of the black box nature of the LLMs. Still, they record a statistical profile of billions of potential dependencies amongst things, which is where their value comes from. But I can't correct them. If I could correct them and make adjustments to statements of dependency, then one could expect to reduce the number of errors, including errors in logical reasoning. Does that make sense to you?
That totally makes sense. I think that's two different paradigms. Like people try to solve problems of large language models. For example, from my side, I'm more like thinking like using large language model as maybe a proposal distribution, and try to use some external machinery to analyze and utilize the proposals of large language model.
Yes, I like that very much. I like that very much. You're not counting on the large language model to do reasoning. You're counting on it to be able to provide support for structured reasoning of the kind you're doing. Yeah. Okay.
And I'm indeed aware, but I'm indeed aware of the people working on the other paradigm where they try to hack into the structure and representation of large language models and try to figure out what kind of knowledge, how the knowledge has been stored in the representations, and how can you edit the representation such that you can systematically crack the behavior.
Yep. Okay. Thank you.